Okay.
But it's kind of the equivalent.
Yeah. They just don't want to abuse notation.
Yeah, I see. It follows that F equal to sum over, direct sum over X in G of ZX is a free abelian group, right, with basis B, which is what? Bx, X and G. I think that makes sense.
By definition.
Yeah. Now he constructs a map phi from B to where? To G by phi of Bx equal to X. Okay. Is this surjective? Yeah, I think so. So since that's surjective, it follows that the homomorphism phi tilde. Let's see here. Oh, I need to have the right picture in mind, right? So you got this free group. We just constructed it, sort of. We thought about constructing it, and the basis is included in there. We constructed this snazzy function phi over here to the group G, which was given, and so by part one, there's a phi tilde, right? And if this guy is on 2, if phi is on 2, then certainly that is also surjective. And so then what?
First isomorphism.
Then first isomorphism theorem. Very good. So G is isomorphic. I feel like I'm fall over. G mod the kernel. What is the kernel?
Or F mod the kernel.
Oh, F, I'm sorry.
Phi tilde.
Mod the kernel of phi tilde. Oh, and that's the R. The kernel phi tilde. That's the R. All right. So he says this is basically extending by linearity, right? So, all right. I'm going to read the rest of this because I want to. Well, I'm going to read the rest of this because I want to start next time on the actual stuff. So we have a few minutes left, and I think you guys will understand. I think, well,
Already read it.
you know, well, I'll shut up. So he says, an abelian group G has generators B and relations delta. If F is the free abelian group with basis B, and the relations are a subset of the free abelian group, right? So in other words, the relations are between words that you know about. And they're formed by integer linear combinations of the basis, right? And
Thought you'd like to know if the zeta function is hanging in full glory. What's the
oh, the zeta function is, well, oh yes, very. I will have to come investigate momentarily.
Well, I might be leaving soon, but you know what? You've seen
I got a
it before.
flashlight. I can, and you can't. I mean, I just flash it.
I'm gonna paper over the door before I leave.
You go with time. Is this amazing? Like zeta, like the Riemann zeta line. It's this poster. It's like 8 feet long.
Oh goodness.
You know, for the Riemann zeta. Like it's great. It's great. All right, so it's a good thing he didn't see us misusing the ZN notation. All right. Okay, so
Misusing it? So you do p-adic stuff?
yeah. Analytic number theorists like p-adics are like they're, I don't know. It just comes up in ways I don't understand. But there's a whole. We should do an independent study on. I need to decide if somebody do an independent study on p-adics sometimes because I'd like to. There's all kinds of weird. There's like some weird norm in there, and it's very much like real analysis, but very not, and very. It's again this kind of weird mixture of algebra and analysis, but things I haven't done. I think it might open new ways of me thinking. But anyway, I shut up. Okay, so anyway, if you've got generators and relations, this gives us a presentation, right, of the abelian group. Theorem 4.2 is pretty awesome. Given a set T, there exists a free abelian group F having T as a basis. So what this means is that you can take any set you want and you can just start adding stuff in it, and it makes sense.
It also means that the free abelian group functor is adjoint to the forgetful functor from free abelian groups to sets.
Ah. I would not have seen that. I was following his proof pretty well right until the last sentences. The theorem is proved by first using a scissors to cut out the b sub t's from F, and then by replacing each b sub t by d itself. One can be more fussy here if one wishes. So I haven't had a chance to further investigate the fussiness which is missing here. But, and then we'll go on here. Theorem 4.3. Mostly we're just going to use these things on singular simplicities and so forth next time. So, any two bases of a free abelian group F have the same cardinal. So that allows us to use the cardinality of the basis to define dimension, if you will. I don't think he calls it dimension, though. I think he calls it rank. Yeah, rank. And so if you have two bases of a vector space over any field, they have the same cardinal. Well, yeah, that's actually the... Actually, so in the finite dimensional case, that's what we do in the 321 course, right? Where we should just counting. But here this is interesting. If it's infinite dimensional, one uses Zorn's lemma to prove that basis of V exists, and then one uses set theoretic fact that family of all finite subsets of an infinite set has the same cardinal as the set itself, to prove the invariance of the cardinal of the basis. And then I don't entirely understand this last paragraph here. Do you guys understand that last paragraph in the proof of theorem 4.3? It's like A and B be bases of F for a fixed prime P. It's easy to see that the quotient group F mod PF is a vector space over Z mod PZ. I guess that's a finite field, right?
Isn't F mod PF isomorphic to Z mod? Well, I guess not necessarily, because it could be any free abelian group.
Oh, right.
That's what's confusing me.
Oh.
Yeah, so if it's...
Huh.
Yeah, that makes sense then.
Okay.
Because if it's Z, then they're the same. If it's Z squared, for example, then you can see it's a vector space. It's essentially Z mod PZ cross Z mod PZ.
Okay.
And analogously for any other free abelian group.
That's good. I should always think about the free abelian group being like Z to the power n. There, fix that.
Or Z to the ordinal.
Or Z to the ordinal. Let's not get carried away. All right. Is a vector space, and the cosets A plus PF form a basis. Oh, okay.
Who would be cardinal? I guess cardinal. I don't know.
So the dimension of that is because that's the number of finite subsets.
What is?
Well, he's using this. The family of all finite subsets of an infinite set has the same cardinality as the set itself. So these cosets are a family of finite sets. Is that right? A plus.
Huh.
Well, I don't know. I'm not sure I entirely understand this proof. I'll just say that. Let's go on.
I mean, that's definitely true for the case of natural numbers, right?
Yeah, there's something here I don't understand, but I must go on. I want to get to a certain point here, and I only got 2 minutes. So, definition: if F is a free abelian group with basis B, then the rank of F is the cardinality of the basis. That agrees with our finite dimensional, and it gives us some notion of infinite dimensional. Well, dimension. Sorry, rank. Anyway. So an abelian group G has possibly infinite rank R if there exists a free abelian group F of G with the rank of F being R, and G mod F is torsion. What's torsion?
The part of the group that is finite order.
Right, it's the part that has no infinite cyclic subgroup. Zn's pure torsion. Z sub n is pure torsion. Yeah. And that brings us to the next section, which is the singular complex and homology functors, which is where I will start next time, and hopefully get a good ways into. I love this sentence he has on page 62, talking about orientation of an n-simplex. He's like, an orientation thus gives a tour of the vertices. There's so many great sentences in this book. It continues to, I enjoy it so much. A tour of the vertices. It's a great way to say it.
That's actually a technical term in graph theory.
Oh no. Oh.
Although also that terminology in graph theory is very varied. Like different people say different things, but there's tours, there's trails, there's walks.